Thanks a lot for your attention. My name is Peng Cheng. Well, I am a data engineer in the daytime and a drawing engineer at nighttime. So you are going to see a lot of references to drawing in my slide. I'm not sure if it's the most appropriate example, so please tell me if you have a better one. The paper I'm going to present is the tensor field network, but well, I would call this is some kind of literature review session because the paper is actually summary of many ideas, most of which exist in the past 2 years. So the core concept is what we call the group convolution or G convolution, which is a generalization of the conventional convolution. This is where we're going to start the conventional convolution network. Well, right now, it appears that most people are, have only started getting to machine learning after the concept of convolutionary network has been proposed. So most of us take it for granted, and we will start the talk by trying to figure out what's the nature of convolution and why is it so important. So we start from an era where the convolution network didn't exist. So this is before 1987, and this will definitely happen again. So don't sit there too comfortable. And because a lot of people have been kind of persuaded by the universal approximator theorem. So in pursuing of unbounded representation power, they always start with fully connected layer, which has the most number of weights. And so to their opinion, this is equivalent to being the most powerful. And in case you haven't remembered, this is a fully connected layer. And people quickly figure out that's not the case because the fully connected layer is not, is not smart to generalize many things. This is one of the examples. You probably won't see images like this very often, where people are being upside down. But for the fully connected layer, because because all the weights are not necessarily correlated with each other. So this effectively means even if you move the portrait around, then because there's no correlation between weight, the layer will quickly overfit onto the training image you feed to him, and basically optimize into a local minima that that is prevalent in your data set, but actually it's not very common in real case. This is one of the example, and it's kind of rare on Earth, where you can easily use gravity to figure out the right direction of the portrait. But we have several other cases where it will definitely fail. For example, where gravity doesn't exist, or the direction of the gravity is perpendicular to the camera. And so, to mitigate this problem, people quickly resort, before 2012, people quickly learned to resort on invariant feature, which means they handcraft a feature that regardless of how you manipulate the image, you will see identical result. And this seems okay if you just want to apply it to the first layer as some kind of handcraft feature for image recognition. But for neural network, all things break apart because your architecture, your constraint on the filter pattern are also supposed to be applied to the high-level feature after the first layer. And if your output becomes invariant after the first layer, then the later layer won't be able to, will simply ignore that part of information. And a common example is what we call the Picasso effect. This is some kind of artwork that is similar to Picasso's style. If you use invariant feature, it will quickly be recognized as a common human face. For any animals, this will just be absurd because, if you don't, if all the spatial relationship after the first layer, where the feature of eyes, the nose, the mouth are ignored, and you put them together, it pretty much becomes a bag of words. And if you simply throw them into the pool of the high-level feature, then a human will quickly recognize that it is not a normal human face, while the machine won't be able to recognize that. So a slightly better idea is dot augmentation, where assuming you have unbounded computation power, what you do is you simply take an image and try to manually generalize it by copying it so it's spread everywhere and it covers much a real case as possible. And the good news is that it kind of works, particularly if you're using a convex optimizer, for example, like a support vector machine, because in this case, the random augmentation will make the optimizer converge theoretically probably equally fast. But, well, obviously, it's already 2018, and I think, well, it's just not cool anymore. Regardless, the idea is not bad, and despite being much less efficient for deep neural network, people are still using it. And if they feel it's too slow, they just buy more machine. This is basically their altitude. Yes?
If this is a discussion point, we'll refer this to later, but my question is, okay, you augment.
Yes.
But is it really invariant over translation? Because technically that data point is a separate picture. Like if you have my picture as a person,
yeah,
and your classes are person, animal, whatever, or face, animal, and then you pick me up as a person, and then my rotated picture will be also picked up as a person. There is no link between the two, although they're the same person, right? So that information is missed if you augment the data, if that makes sense.
Well, if you augment both the image and the labeling, then you still can retain that relationship. Well, I'm not sure if it makes sense for example, the face recognition task where every face has an identity, but I think I can give you a more complex case. The autoencoder. If you're training on autoencoder and to make it generalizable to rotation, then obviously you will rotate input and output at the same time. We'll get to this example later. But basically, there are numerous ways to augment a data set without losing this information. I'm not sure if that answers your question. Okay. So, and starting from that point, people invented all kinds of ways to augment data set. Which means, good business for NVIDIA, which means they have 2D translation where they augment it in 2D, which is, kind of slow, but all right. And for the case I demonstrated before, when gravity doesn't exist or, is irrelevant, then on top of 2D translation, you also have 1D rotation, which is, a bit slower, but still acceptable. And now, that's the real hairy part, the 3D rotation. This is the output of a fisheye camera. Theoretically, you have the same dimension as, 2D translation and 1D rotation, but if you augment the data set, you will get a lot of numerical error because you have to interpolate. And now, this example is what we have encountered in a recent challenge, proposed by the AI Robotic Racing League. This is one of their gate. So when this data set is published, it's kind of interesting because I didn't discover this immediately. One of my teammates does. He immediately pointed out that first, the gate is carved from a cardboard, which makes it planar. So, and the second, all of these pictures are captured by handheld camera. So that, basically means you can't find any picture of the gate from a bird view or from beneath, which makes it hardly to generalize. So what one of the solutions we did is to augment some of the pictures like this through 4D affine transformation. I assume you know what affine transformation is, right? And this is the basic of the linear algebra, which makes our first year very miserable. And this is the crown jewel of augmentation, 6 dimension. 3D translation, 3D rotation. I'm not sure any GPU is capable of doing this because even a small range will incur a huge data set, which makes any training infeasible, which is exactly the case where the author of that paper has encountered because they're dealing with 3D structure in material science and large molecule. So this is kind of similar. And finally, my favorite case. Yes?
Quick question over there.
Absolutely.
Yeah, sorry, just a quick question. When you do anything beyond 2D translation and rotation, is it necessary for it to be done like in a simulation, or like how do you, if your data set consists of 2D images, you can't effectively do a 3D rotation, for example, right?
No, I can't. But this is not an image. This is point cloud.
Yeah. Oh, I see. So this is for point clouds.
Exactly.
Okay. Thanks.
So far, fortunately, I haven't touched this part yet. This is the relationship between altitude and the flight characteristic of fixed-wing aircraft. When you're higher, when you're higher in altitude and higher in speed, basically the handling of the aircraft will be similar to as if you are at lower altitude and lower speed due to lower air pressure. So at that time, you're reading your airspeed reading through the pitot pipe will be inaccurate. It will be referred as IAS, indicated airspeed. And in this case, everything, for example, your minimum turning radius, your allowed flight envelope, all of them will change, yet completely predictable. So, yeah, this will represent a very hard case to augment data set. But again, right now, none of the paper I've present, in the reference list will be dedicated to solve this very niche case. It will be, a kind of a discussion point later. So, we'll see a plethora of data augmentation, most of which are invisible or cost a large number of computation resources. So, the question here is that, how about a better idea? We just enforce some kind of constraints on the architecture of the network to the point where if you feed it one training image, it react, it evolve, it adapt as if you have fed all the augmented image to it. If that happens, that would be nice, right? So, and I'll just jump to the conclusion directly. It definitely exists, and for most of the augmentation cases, it is generally called the GConvNet, or Group Convolution Network, and all these papers that I'm going to present are a special case of it. And so, for the first part, let's do a quick experiment. I know you are against me doing this, but I think it's simple enough.
Is it possible to make this bigger, or not?
I think this is the biggest.
Okay.
So we'll just start from hello world example. We have a data set of we have the common data set that we all know of, and we augmented beyond necessary. We just push it around and enforce some kind of cyclic relationship. So it looks like the augmented data set becomes this. Every image becomes 100 image, and we feed into a residual network that has a special special architecture designed such that its settle point is minimized, and we don't use initialization. So at first, all the weights are 0, as you can see. And then when you train on the raw data set, it will the train layer will correctly identify the pattern, which looks like this, but obviously it will suck if you just move the test data a little bit. And now, how about we train on the augmented data set? This is what it looks like. Fully connected layer without any convolution, convolution constraint, yet it demonstrates the symmetry that you've all been familiar with in the textbook. So, this gives us a little bit of hope. And now, to explain this, we start from the concept. We start by trying to define the data augmentation analytically. The nature of the data augmentation is simply a unary operator, where you can apply it to a signal, whether it's sequential or a 2D image, or some kind of 3D point cloud, and then so it becomes another kind of signal. So And one of the conclusion by making this by using this I'll just jump to the conclusion of the conclusion of the the analysis of the augmentation as a mathematical concept. The conclusion is that if the augmentation satisfy both transitivity and group equivariance, what will happen is that a fully connected layer will always collapse to a group convolution layer, which is very similar to a conventional convolution layer. See the similarity of this term and this term. This is just convolution, and this is this is the group convolution, or G-conv, where this term is replaced by the augmentation itself. And for this lemma to be applicable, you first have to ensure that that both the transitivity and group equivariance conditions should be satisfied. The transitivity is kind of easy. It just means given any point on the domain of the signal that you want to augment, you can use this augmentation as some kind of carriage. It means if you have a point on the signal here, and you want to move the point to another place, you can simply use a convolution to move the entire canvas. So that point, the starting point ends up at the other point, and this has to happen for any point on that signal.
Thing.
Yes.
That formula, like if you scroll up a bit,
yes,
you showed a formula. That one. I didn't quite get what was happening there. Can you explain that again? The one that says looks familiar.
This is the definition of convolution, right? Sorry, I kind of abused the notation a little bit. This means the dot product of two functions, which means if you slice both functions into many small pieces, they are kind of similar to high-dimensional vectors, and the dot product is just dot product in the sense of where you treat those functions as high-dimension vectors.
Maybe to clarify a bit, it's like the dot product is like a sum in the case of in the usual case in machine learning, or it can be like an integral. If instead of having like a discrete windows, you actually have like a continuous image and like a windows that's totally continuous. So that's just the notation of this scalar product. And otherwise, then you can recognize, I guess, like the convolution is just like that's sort of the definition, like the sum of like a function with like a weight. The weight here, W is the kernel.
So the knot in between in the first equations where it was highlighted, is that a dot product or is that a convolution?
Oh, this simply means applying the augmentation to the signal. This is an operator, and when this is applied to a signal, it means the signal is being augmented, being pushed around for more generalizability.
Should augmentation apply to the X itself?
That's a subset. Good question. Actually, if that's How do I describe this?
Maybe, yeah, if you want, I can try if you want.
Sure, no
Like,
problem.
Yeah, like the augmentation is something that you apply to a function. So for instance, like there is translation. That's like one of the main augmentation. And so you translate a function. So you have an image, and like you translate your image.
Yes, but isn't X the raw data of the image itself?
Naturally, it's like
X is the coordinate, is
Yeah.
the
Oh, I see.
domain.
Oh,
Yeah.
okay. Makes sense.
yeah, exactly.
And then did I get it right? So that plus over there then is a dot product?
This one?
Yeah. So you said something is a dot product.
Oh,
I'm-
sorry.
I'm looking for that.
This angular bracket is dot product.
Oh.
That's physics syntax.
Ah. Okay.
Sorry, how am I supposed to write dot product?
Thank- fair enough.
And so just to clarify these, this step that you're showing is a demonstration of the MINS data set that you were showing earlier, where you did enough augmentations and that the
Yeah.
fully connected layer collapsed into like a convolution layer.
Exactly.
Okay.
And how are you tracking that it collapsed?
Well, this is after like
A few minutes of training, and
Oh,
I didn't.
by
yeah.
visual expansion.
Exactly.
Visual
I didn't.
expansion.
I didn't enforce any
Fair
like constraints. I only I only augment the training data set, and this doesn't even converge completely. You see, these are I don't know what these are. It's probably numerical artifact, but basically you can already see the pattern.
So you're saying that there is a convolution window, sort of as an artifact that's moving around, and why are they in sequence? Like, is that what was that like? Is that did that happen in data, or you just?
Oh, these are weights dump. These are you finish training and you save the model and you extract every weight from that model and
No, I understand
eventually,
that. Yeah. So the question is that there is I see a filter.
yeah.
Similar to convolution, whereas
Yeah.
you can call them filter,
Yeah.
moving sequentially as you would in a convolution layer.
Yeah.
They seem to be neatly in sequence over here. How did that happen? Because like I don't think fully connected layers do have that.
These are, wow, that's a very good question. I've been pondering, I've been trying to bypass the phenomenon you described for a long time, because for a fully connected layer, if you train without initialization, then you will stay at the saddle point forever, right? And if you initialize randomly, then generally you will get a very some kind of filter that is heavily disturbed by the Gaussian noise. So what I do is that I didn't use the fully connected layer, and I didn't use residual network either. I use a very weird network architecture that is presented in NIPS 2017. And it is mathematically proven to minimize the number of saddle points. So it doesn't matter if even if you use it without initialization. So it's kind of interesting because the fully connected layer is like without this part, right? And a residual network is when you have another linear layer, and then you skip this and the other layer, and then add another ReLU. This is like somewhere in between. So basically, you have saddle point either residual network or the fully connected layer, but you have very little saddle point in this architecture, which is what enables me to observe that pattern. And anyway, yes, and we'll get to this part later in the discussion. Can I proceed?
Yep.
So now let's talk about the equivariance. And you mentioned to retain the relationship when you're doing the data augmentation. And equivariance is kind of the attempt of maintaining that relationship. For example, if you're doing data augmentation on masked CNN, obviously you will augment the image and the mask together. And if you're doing an autoencoder, then it becomes more obvious because, well, you know, for trivial reason, you have to when you shift the input, you have to shift the output, and the plain old equivariance actually refers to this kind of relationship where, you know, the sequence of applying a neural network pipeline can be swapped with the augmentation. And if you think this is some kind of, you know, way too meta, then I have an easier example. Think of SQL predicate pushdown. When you're doing data cleaning or some kind of simple analysis, when you have to filter on top of a big data set, what you do is you first narrow down the range. So yeah, that's a good example of equivariance. Basically it means an equivariant operator, in this case, the processing pipeline can be swapped with another operation. That means you can either apply A and then B, or B and then A. The result are equal. If it has that property, that means the compiler can just optimize your query. But, well, that's a different story. Basically, the equivariance is a special case when we're trying to use the masked CNN and autoencoder. But this is not, this condition is too strong. For group equivariance, it's slightly weaker. It simply means that you have a lot of augmentation that forms a group. You don't know how big this group be. You don't know exactly what the nature of this group is. You just know that there is there's presumably a collection of augmentation where regardless of which one you choose inside of them, then for the next layer you can always find another augmentation in the same group, and which allows you to retain the kind of information that has been incorporated through the data augmentation process. So
you might want to go over that again. That's because that's a very that's a very subtle mathematical point that you're making, right? That as long as you have another operation that's still preserving the same group structure,
yeah,
from layer to layer, then you're going to preserve the operation. But that
yeah,
it might be worth elaborating on that a little.
How about group without structure?
What's that?
How about group without structure?
A group with no, just
it's
an operation with
totally chaotic.
Yeah.
Cluster of augmentations. You just know exist. You just know that it exists. It can be arbitrarily large, but you don't care at this point.
That's
yeah, because the only thing that it helps you is that you don't have to, when you invent the first layer, you don't have to invent the second layer again.
What do you mean you don't have to invent?
Because this augmentation and this augmentation is in the same group, and because the output of your first layer is the input of your second layer. So in this case, if you can devise some kind of general rule that applies to everything in that group, and this group just happened to include the first augmentation and the second augmentation, then this problem is pretty much solved. You already invented the optimal architecture to handle all the, well, whatever augmentation that you could possibly afford. So it's kind of, you know, I think you're right in terms of it is indeed a very complex concept, but the intuition behind this is simple. It simply means if you can't find a rule for a small collection, then it doesn't matter. Can increase this collection a little bit, find a rule that is applicable to this bigger one, and if it works, then your problem is solved. You know it automatically you know it is automatically applicable to the smaller group.
Right. So you're saying on the basis of a containment relation,
Yeah.
right? You can guarantee that you're going to preserve the structure that you're interested in.
Yeah.
By just picking a larger set that includes it.
Yes.
Yeah.
And we'll get back to this part later.
So, what makes a group of augmentations like in the same group? Like, is it sort of like linear transformation as well as a group, or what?
For good old convolution network, yes, you're right. They are transformation, and the augmentation just happen to be also transformation. But in this case, this is kind of, you know, it's kind of an outcast in the general family of gconvnet, because none of the other subclasses fits into this pattern. For example, for the gconvnet that, factors in both translation and rotation, the input is clearly have 2 dimension, right? And the augmentation has 3 dimension. Rotation, yeah, contributes to extra 1. Yeah. So that means this is kind of intuitive. The output of the first layer is also 3 dimension, and the augmentation group as well.
So what you said, so rotation is like a group of convolution, translation is another group, or like, is that what you mean?
Look, you can always run a Cartesian product of 2. You can always run a tensor product of 2 group, and that becomes another group that includes both groups.
Yeah, it is. Like it's not a convolution, but like for instance translations, it's like a group. Rotations, it's another group. So it's like the set of all possible groups of a given space in like n dimensions is going to be like a group.
Okay.
So you can think like usually when we think about rotations, we think about it like in 2 dimensions, in 3 dimensions.
Yeah.
But you can also like sort of generalize that notion, like those kind of groups in n dimensions, and have like a linear transformation between like this group in 3 dimensions and this group in like sort of further dimensions. So that's what we call like representation of groups. And that's kind of what we're doing here. Is like, so the input should be invariant through like 3D rotations. And we want that like at the further layer, all the layers are also invariant through that kind of rotations. So there should be like a sort of linear function between like those rotation on one layer and the rotation on the other layer. So you can always find.
So just to be clear as well, we're not talking about a group as in like a set, right? Like is a set with particular structure that's sort of like addition, right?
I think group is just associative set. Associative monoid.
Yes,
like,
but monoid.
Okay, that makes it even
clearer
worse.
necessarily.
Makes it even
Yeah. Yes,
My bad.
Associativity
You're right.
is an essential part of that.
I prefer to think it as this way. When you only have this, you don't necessarily have to figure out what this is. You just assume that they are of the same category.
That's the augmenting arrow.
Exactly.
Yeah.
Yeah, and with that in mind, you can defer the the reification of this part, you can figure this part much later, just by, just by studying the nature of this and how it looks like in this layer. In this case, for example, in the 2D translation and rotation case, the output, because the augmentation is 3-dimension, it turns out that the output is also 3-dimension. And it turns out that when you choose from this, you need to know that the augmentation must be capable of augmenting a 3D data as well. And then you realize that, well, we are lucky. If this is 3D, 2D translation, and 1D rotation, then, and this is also 3D, then it's merely translating twice and rotating twice. You don't lose anything.
Or you do data augmentation and you end up with the same representation in the hidden layers, like with, for example, max pooling.
Yes. That means you have like that means how do I explain this? You rotate, basically you have different path of reaching one rotating angle. That is correct. But you don't lose information. Because, how do I describe this? If, well, this is, related to the concept of filter bank. If you have many filter banks, many channels that eventually merge to the same output, that basically means you can just merge the weight as well. So in this case, if multiple path of rotation and translation eventually leads to the same point on the output, then it is safe to merge them. Not, well, let's get back to this part later. So, for the part of you that is really like quantitative, there's a simple proof here, and we also have a more elaborate proof. Now, all the paper I'm going to show you are just a subset, a concrete example. Yes?
Can you hit Control plus? Like, will that make it any bigger? It's like I can't quite see.
Wow.
That might be better. Yeah.
Yeah. Nice. So all the paper I'm going to present you here, including the tensor field network, are just a concrete implementation of this idea on different domain of the input data and on different types of augmentation. So keep that in mind. First, we have. Oh, and by the way, sorry. This is exactly the point you brought up with the when you devise an augmentation for the input, then you can almost be sure that all the data except the input layer, all the high-level feature, should have the same dimension as the augmentation itself. And if you want to stack augmentation further on top of it, you need to make sure that they're compatible. So, for the convolutionary network that we're all familiar with, this is a rare example where the input space is 2D, the high-level feature is 2D, and the augmentation is 2D. Sounds quite simple and straightforward, and the convolution process is just the, just replacing that aug operator with with the with the delta that push around. We've all seen it, and now we start getting the interesting part. The group equivariant CNN proposed in 2016, which is a very simple case. It only adds 4 extra rotation, all of them 90 degrees, on top of translation, which means it eliminates need to augment the data set through 90-degree rotation, which is not much because you can just buy 4 more times of machine and get the same result. But still, well, it's just the beginnings of a long series of breakthroughs. So for the filter bank part, I think this diagram pretty much answers your question, which is how different paths of augmentations can be merged together.
What is the diagram showing us?
Well, this is the architecture of the group equivariant CNN. It has 4 channels. Basically, you have an image, and first you rotate it to 4 different angles, and then this is the interesting part. When you devise the next level, high-level feature, yeah, well, the result of different paths of augmentations are dumped together. For example, if you first don't rotate it and then it runs through the weight, and to get the high-level feature of the first layer, and then then the feature is rotated for 180 degrees. It will end up here. And if you rotate it 90 degrees twice, it also ends up here. And you know that the result can be merged safely because this is already you already know that this 180 degree already captures all the information. So it no longer matters which path that the it gets this number from. I think this is what you're referring to, right? Okay.
So just to be clear, that's not an explicit representation of the neural network, is it? Or that's a representation?
No, it's not
okay,
explicit.
Yes.
Well,
that is a representation of how the structure of the representation could change as it's represented through the different layers in a single neural network.
Exactly. More specifically, a filter bank.
Through the filters, right?
Yeah, this is a filter, this is a filter.
Okay.
And this between this is a rotated image, this is a rotated feature.
Right.
So I think my question is, do rotations occur deterministically or they're learned by the filters?
Deterministically.
Okay, so that's the first sort of layer.
Yeah, because, it's to be honest, it's not a very practical paper. You just have like 90 degrees rotation. And I think comparing to the time to read this paper, most people would prefer buy 4 times of machine. 4 times more machines.
It's simpler.
And probably cheaper. And let's proceed. Yeah, this is the end of it. And now we're getting into the heart of the beast. The harmonic net. Input, still the 2D image, high level, augmentation, translation and arbitrary rotation. And if you represent it in the filter bank, as in that 2016 paper, you get a huge filter bank and lots of weight. Probably most GPU won't be able to hold it. that's where the spectral decomposition becomes vital. It's an old idea, but still kind of makes sense here. Basically, the idea of spectral decomposition is to represent a filter in high dimension, in this case, many filter banks that are arranged sequentially in their rotation order. If you treat this high dimension filter as some kind of function or a very high dimensional vector, then you can find a bunch of orthogonal bases that can vastly simplify compress the data used to represent this filter and accelerate the convolution. The computation of the convolution. Yes.
So sort of what you're saying is you're going to handpick your filters, right? But you're going to do it in a way that has a sort of mathematical elegance to it that allows you to handle the complexity or the size of the space that you're interested in this case, arbitrary rotations.
Yes.
Right? In a way almost like Fourier analysis style way. Is that the sort of...
Exactly Fourier analysis style way. Sorry about the equations, but basically the idea is to show that first the orthogonal basis doesn't exist only for vectors. It exists also for function in 1D or 2D, which is the 1D or 2D Fourier basis. I'm sure most of you already know, and it doesn't stop there. It also, because all the filters on any dimensions will only become kind of, robust if it only contains low-level information. You don't want your neural network to screw up when somebody just added some kind of high-frequency pattern to it. Right? So that means if you use Fourier transform or in this case, the spectral decomposition, you can only, we can retain the nature of it while discarding most of the high frequency information. So spatially, it saves the space to the memory to fully represent filter in high dimension. And
is what you're saying is that you're more likely to have noise in the higher frequency ranges?
Yes. And in terms of computation, it's just a good old convolution theorem. The convolution in the time domain is equivalent to pointwise multiplication in high frequency domain. So that means the convolution process will also be accelerated. And so as a result, it becomes the algorithm of harmonic net, because it gives example of the harmonic basis on the rotation, which means it doesn't cover the translation. That means the first thing when you receive the image is to take a slice at at each patch of the image and convert it to the frequency domain. So later, when you so basically it's like the filter is kind of an amalgamation between the image domain and the frequency domain.
The Fourier series they use in the paper looks like this, but it's actually
kind of underrepresented, because the real Fourier series looks like this. It also contains the, an extra dimension on the radial part. And
So in order to take the Fourier series of an image, you're gonna have to take some portion of it, right?
Yes, that's a
some
patch.
slice.
Yes.
Patch.
Yes.
So is it like n by m patch?
yes.
I'm assuming. Can you?
Well, it's not directly, it's not explicitly shown here, but in the, in the architecture diagram you can see here, after the GFT, this is, each filter is still three-dimensional. This contains 2D dimension on, this contains dimension X on the image and dimension Y on the image and the radial dimension. And
Was your question how many patches there was going to be, though?
Yeah, I was thinking there could probably be one patch for every decomposition, or is it like multiple patches that give you the
there are multiple patches.
orthonormal? And so do you? So okay. So what's a typical size of a patch? Do you know? 10 by 10. 20 by 20, 3 by 3?
It's either 3 by 3 or 5 by 5. In the illustration of that paper, it's 3 by 3.
Okay, so in that case, the bigger the difference between adjacent pixels, the higher is the frequency, right?
Yes.
Okay, so at that point, if you want to extract these basis vectors,
Yes.
In the frequency domain, are you like trying to optimize, or are you? I cannot see how you go from a patch to orthonormal vectors in frequency domain.
Well,
And you don't have to go into detail, but just something high level, like how do you go from here?
Well, this is my understanding. Because the network is designed to be equivariant to both translation and rotation.
the way I see it, the the GFT only handles the rotation part. The translation part is still handled by, replicating that filter everywhere on the image, and it sprawls everywhere. And the result of the convolution is still interpreted as many dot product locally.
Except that in this case, because the result of the convolution is is already in the frequency domain, so the output of each layer
Is a complex number. That's the only difference.
I think, wasn't your question is how is he coming up with the filters?
Yes, in the end, based on all these patches.
So I think
For
it's more
example,
just
yeah.
how are you choosing, how are you actually choosing your filter bank? You said you were hand picking it before so that it matches a spectral thing. You're dropping the high frequency domains.
Yes.
I think it's just analytically.
Okay, so there is some optimization, like in trying to.
But like optimization in the sense that they just sort of assumed that the high frequency domain is going to have more noise in it. This kind. I mean, we might want to take this afterwards, but they just picked it analytically.
Okay.
For example, this is a typical filter bank, and you only pick these two.
You.
That's it.
Oh, okay. That was like
0,
2.
yes. 0 and 1. That's it. And on the radial basis, you still need to pick a lot. Which is the part that the original paper has illustrated poorly. But what happened is that whenever it takes a filter bank, it has to be replicated. It has to be translated until it sprawl everywhere over the picture.
Okay, yeah.
And it still calculate the correlation.
Yeah.
But yes,
It was just more. I think it was just more an issue of like how or where were the filters coming from.
Yes. I get it.
But we got that. I didn't realize there was only two, though, myself. I didn't realize they were only using two of them.
So,
And so this, in this case now, the left side would be the left one, the left filter set, and the right side would be the right filter, or whatever, or vice
yes,
versa.
and remember, each output of this of the channel is a complex number.
Right.
So when you move from one rotation order to another rotation order, it's kind of you multiply two complex number together. So the rotation becomes the frequency of the basis becomes faster. So in this case, this is the slowest basis, and this is the slightly faster basis. And when you multiply a complex number, it's like making it a bit faster.
Right.
And if you already have a fast one, and then you multiply it with another basis which is rotating on the other direction, then you get the slowest one. Basically,
As you
it's
climb,
kind of similar to that paper that shows 90-degree rotation, except that in this case the two filter banks are components of the Fourier basis with different frequencies. This is the slowest, this is the slightly faster, and you can still assume the result of the convolution into the same filter without losing any information. And after that, we get into the first paper that ever gained mainstream attention from this school of interpretation. All the papers before this have suffered similar fate. Basically, the author tried to submit it everywhere, and the review was always like, to mathematicians, this is kind of a bleh, and for machine learning researchers, they prefer buying more machines. So and this is a rare case where it has attracted enough attention to make it the ICRR 2018 best paper. What happened is that it fits into a very niche case, the situation awareness of mobile robot platform. For Tesla car, you can use a lot of cameras. This is a Tesla S or Tesla X, Tesla S or Tesla 3. Well, you can use a lot of camera to identify everything happens around you, so the car doesn't have to turn its head. Well, it doesn't have any head. Or you can just use a fisheye camera. But so far, this hasn't happened. I would argue that the technology to enable autonomous drone flight is already mature, but it hasn't happened so far. What we have right now is just a drone that is pretty much stacking camera as if it is a car, on 6 different directions, because the drone also has to look to the upside and downside, which makes it very very unnecessarily. And one of the drone that was launched by 2 ex-Google engineer is called Skydio R2, and it has 12 cameras for stereo visions. So yeah, this is Skydio R1. And I remember the drone was released in 2017, and I guess that explained a lot, because by the time it started research, that paper hasn't been published. So theoretically, it becomes much easier. Oh, sorry. Actually, this is Skydio R1.
not too bad, but still, it gives it a staggering price tag of 1,800, and yeah, I guess because the industry is like moving too fast. I'm not sure how they keep up with this. So, the spherical ceiling is used to tackle this interesting problem. Basically, you have a fisheye camera at the center of the drone, and you have like visual cues from everywhere, and you are not allowed to move around. You can you can only rotate inside the visual ball that the camera has projected, and you want to figure out what is around you. And this basically means all the conventional translation, all the conventional convolution becomes useless, and you have to somehow rectify them to different direction, and which is just not efficient. And this paper is smart
in that it tries to use GPON to only handle that rotation without translation, and it turns out to be much easier than we thought. We only have the rotation group,
and the input is on a sphere, which is 2D, and the augmentation is 3D, because only 2D. It's like 2D, and plus a yaw angle. Well, I'm not sure how to describe this. Basically, you have, there are many different ways to rotate a point on a ball to another point on the ball, and
that all different kinds of way contributes to an extra dimension. So, as usual, it will use harmonic series. In this case, for the 3D rotation will be a Wigner D function. I don't know what it is. I have no way of visualizing it. I've been told that if you just remove the yaw part, it basically collapses to a 2D function that pretty much that can be projected on the ball. That looks like this, but seriously, I don't have to care. So, and the benefit of this is that you don't have to replicate the filter everywhere, because only rotation is allowed. So, this means the dimension of each filter bank is only one dimension. This one dimension is the radial part of the Fourier series, and obviously you need different frequency, but that's all of it. This makes the process extremely fast and extremely compact, and yeah, I think one of the reasons that it becomes the best paper is that it may change the scope of the robotics. And finally, we got to the most complex example, the tensor field network. Input is 3-dimensional Euclidean space. Augmentation is 3D translation and 3D rotation. All of them put together, and we are forced to revert to our old pattern, which means we have a filter, and it has to be replicated everywhere, so it sprawls everywhere. And for the harmonic series part, we're forced to use the Wigner D function, and altogether it means when given a point cloud in 3D, it will be converted to a very complex data structure, which has three dimensions for the Euclidean translation part, 1 dimension for the radial of the harmonic, and obviously you have frequency order 0 and 1, just like the harmonic net paper. So this means the representation of every pixel in the intermediate layer of network becomes kind of a tensor, which is where the name comes from. Because you have an intermediate layer, which is a high-level feature of a point cloud, where every point has a tensor attached. And that tensor has one dimension to incorporate the radial part information, and one dimension to incorporate the frequency order. And so, yeah, basically it's some kind of, it's kind of the same principle that is pushed to the extreme. The end is still very complex and very heavyweight network being applied to previously invisible case to enable the analysis of data and network in 3D. But if you break it down in that way, it becomes very simple. So, and after this, sorry. Well, we don't have too much time left. Chris will proceed to explain the virus application that is enabled by this paper.
Okay, so that will be done after the break. Let's thank the speaker.
have a lot of deep discussions with the other facilitators. And I'd like to start off by saying that when first going through the paper, it was really interesting to see the perspective that they were able to give these examples showing some of the applications, but it was really hard to connect in the way that going through the model to be able to get kind of an intuitive understanding of the way that the model works. And as shown in the previous presentation, a lot of their work essentially revolved around this idea of showing that this model has properties that allow you to essentially, given an input, be able to have the same output no matter what the rotation or translation of the input is. So without further ado, I'm just going to go through some examples of what this model is working with here. So this is just an example of what a point cloud network looks like, and it's kind of like the basis of what their data that they're using. So try to imagine you have a 3D object that you can essentially break down that 3D object into many different points. And so imagine you just have this big array of all of these points that'll have like an X, Y, and Z coordinate. And what this model does is it associates every single one of these points with another vector. It could be, in one of the cases they used, they were trying to simulate, do some physics simulations. So imagine, like let's say with this object, if you were trying to simulate its motion, if you, let's say through this object, you could say that there is a velocity vector, like an X component, a Y component, Z component, that would be associated with each one of those points. And that's just to give you representation of the kind of the input. And one of their examples that is probably the most impactful area of this model is in this idea of chemical point clouds. Essentially, what the data sets that they were using was they have the X, Y, and Z component of all of these different molecules, and along with it, they had a one-hot encoding representation of what type of atom it was. I guess just to give you more kind of this was shown in the previous slide, but this is the example. Kind of the same way that CNNs allow you to move an image or create like a translation of an image, you'll still get the same, like if you were to move this image and look at the output from this bounded box, you get the same output no matter where you move it.
Sorry.
And the same thing applies.
Is it video?
Yeah, it was a GIF, but it isn't. I exported as a PDF, so that's why.
Okay, let me show you alternative view.
Oh.
So, yeah. So you
That's
have
fine.
a...
It was already in the previous one, so
I think
it should be
Okay.
it's not worth
Yeah.
effort.
Okay, maybe
Yeah.
I
Thank you though.
Oh.
killed it. No, it's still here.
There you go.
More.
So to try to build up the scale to syncing in 3 dimensions, let's first start in the 2-dimensional view of what type of convolutions are being done here. So if you can think of, these would be kernels in a convolution network. You can see that they have all these different weights that will that are being represented here. This is what it would look like if you were to do like a convolution in, let's say, the frequency domain. And what's really what it was really special when I actually downloaded the code and ran some simulations on the data that we had over at the SGC, and what I found really fascinating about the way that these worked is that with these type of models, you're storing a lot of parameters to represent all the different weights in the kernels. But in the frequency domain, you only have to store maybe 1 or 2 parameters for each one of these for one of these examples. So moving that on to in the same way that convolutions are able to do the translation example, when you do it in the frequency domain, you're able to do the rotational example that no matter how you rotate this image, it will still come out with the same output, regardless of the input that you have. That's the example of why. Yeah.
In the frequency domain, right? So like,
Yeah.
I understand that we're sort of trying to understand it by making it look the same physically, but just to, from my own thinking,
Yeah.
when you're actually, the information that you're extracting is in is in the frequency domain, so it actually doesn't even necessarily have a position in a sense. Does that actually follow?
For this case, because it also has to be equivariant to translation. So
Yes.
yeah.
But I think what I'm trying to say is that this is a metaphor, effectively.
Yeah, I'm just using this as an analogy for when we get to the.
Yes, okay.
Yeah, yeah.
That's all I'm clarifying.
Yeah. So,
Actually, that output, that high-level feature is just one channel. After the inverse GFT.
Let's talk about that.
Okay.
so taking those previous examples that we're scaling now from 2 dimensions to 3 dimensionals, and we want to apply the same idea of looking at applying these like convolutions in the frequency domain. It's really hard to intuitively like wrap your head around how these filters work in the sense that if you were trying to use the analogy of like a convolution filter, or I mean a convolution kernel, like let's say this is an example of one, what these examples are, if you were to have, let's say, an arrangement of points, all centered around this spherical filter, at each one of these points, there would be an associated, let's say, weights that you would multiply with, let's say, your x, y, and z coordinate. And what's great is that this also scales to the vector that you have associated with each one of those points. So let's say you have your x, y, and z coordinate for one of these points that also has an example for like an object that's in motion, a specific velocity vector at that point. You would also have the associated weights at each point in the circle that. So if you were to try to picture this in 3 dimensions, try to imagine that if you had a. Oh yeah.
If you're pointing at the screen, can you use the mouse instead so that
Oh,
people
yeah.
can see?
Sure. If you try to think of this in terms of a 2-dimensional image, this could also be thought of as, try to imagine if you had different kernel weights depending on where you are in the image. So it's like, and as I was saying earlier, what's great about about when you're working in the frequency domain is that you don't actually have to save. Let's say at every single point you have the specific weights that there are at each one of those like points in space. It's just a function that's defined by, in this case, I think it was 2 parameters, and like we said, degree and order. So this is the diagram in their model that showed how their different examples worked, and they had 2 different convolutions, the spherical convolutions that they used that were in the frequency domain, and the majority of their paper, the really complicated math that they had at the beginning that was talking about how these spherical convolutions have those properties of equivariance and that they're translative, that you can move them around and they'll still have the same output. Essentially, they were trying to show that for every single one of the steps in this model, all of those properties still held. So if you were trying to imagine a specific example, let's say you have a molecule going in, it'll be an array of all of the points within the molecule, and for every single point, you see where it is in that spherical convolution and change multiply every single one of their values by the weights that are associated in that spherical convolution. It's a bit hard to visualize, but you actually have, because what was the hardest part for me to understand was when you're talking about models, you usually have to describe the size of the dimensions that you're inputting. Like this can have an arbitrary amount of points that are entering the network because you apply the same filter and get values for every single one of those points. And so that was kind of the tricky part to visualize about how this model works. And so they have 3 separate layers that have all these different aspects to them. And at the end, what they do is for all of those points, the values that they get as their output, they add all of them together. So all of their x coordinates added together, all the y coordinates added together, all the z coordinates and all the like associated like vectors that are along with them, they're summed, and then they're put into a fully connected layer at the end. When you compare this to, let's say, like a deep neural network, the amount of parameters that you actually have in a network like this are very, very small. Yeah, any questions so far? And, okay.
It's probably because I wasn't listening very well, but what's the input? Is this the raw image or is this frequency domain?
Oh, so it would be the point. So let's say an example. Let's say it's like this molecule right here, right? Each one of these atoms will have its like X, Y, and Z component along with what its atom is. And it's just going to be an array of every single one of those points, but they kind of like go in one at a time, if you think about it. Like every single point will have that convolution done onto it. But you can have, like you can put in 1,000 points, or you can put in 10 points, and it'll still have the same thing because you use global pooling at the end.
Almost like they're tokens for a linguistic system, except that you would normally then pipe it back in and make it recurrent, but in this case it's not recurrent at all. Because if you think about it, if you have a point cloud, if I move, I don't need to know any other point. If I move every point and perform the correct operation, all of the points will just end up where they need to be at the end, right? That's the sort of trick of it.
Yeah, and that's where I feel that is the most the beneficial part about a network like this is that you can include an indefinite amount of points into the network as long as they all have the same, they all have the same parameters in each one of the points.
So it's literally infinitely parallelizable, almost.
Yeah. And rotational too. So it's it really fills all the problems that right now one of the biggest applications is in the area of chemical simulations, and that's the area that I'm in right now is working on trying to doing drug discovery in the area of epigenetics. And this is an example of this protein right here, WDR5. It's pretty much the one of the most important proteins in leukemia. That it shows the expression of leukemia. And so if you're able to find a specific type of drug, let's say, like this is a ligand right here, it's like a drug that like a company will create. If you're able to find a drug that's able to fit correctly in here, you can essentially come up with like a cure for leukemia. So that's just like one of the examples of like where this is useful, is that the issue right now is all of these people are trying to model this type of scenario. I can't find a model where you can put in, let's say, 1,000 different atoms within a protein. Like you essentially are working with models where you have a specific defined set of like how many, like what's the dimensionality of your input data, but this one can include like thousands of points. And talking about the results that they had in their paper, they actually tested this with a chemistry data set called QM9. And the results were quite astonishing in the sense that they were very accurate, but it was also a bit misleading because they were trying to do a classification of which atom it was, and I was actually able to run their code that they had, that they showed the results of what they had, and the majority of atoms within like a large compound are going to be either carbon or hydrogen. And so they were getting carbon and hydrogen 99% of the time, but that was like 99% of their atoms. So it wasn't, and also if you think about it spatially, carbon atoms are going to be in the middle and hydrogen atoms are going to be on the outside. So like it's not too complex of a task, but really the most amazing part is what they were saying was that they trained it from compounds that were from 1 to 9, like in input. So they were putting in, let's say, 1 atom and training, or sorry, they wouldn't actually put in 1 because you'd have to have a few points, but they were training it on compounds that only had 9 points, and then they try to scale it up by testing it on on compounds that had like 29 atoms, and they were able to get similar results, showing that they were able to scale it up to like an indefinite amount of input and still have it apply. Yeah, and yes, now we're going into the discussion points. You want to? Oh, okay, sure. So one of the first things that was kind of like glaring to me, especially with that first example, was the only information that they had like embedded into those points was what atom it was. But realistically, if you wanted to get something like it would be insane if they were actually able to classify that correctly if they didn't include some of the chemical properties of the atoms that they were working with. And they didn't really go into too much depth about the data that was being associated with each one of those points. And yeah, we were looking into 3D image sets that can be kind of reduced to point clouds to see if those can be applied in the same scenario here. And also, when we're looking at different types of symmetries, they covered they covered a lot of different ways, like rotational translation symmetry. But if you talk about symmetries within a larger object, like let's say like a small part of it is like rotated, to see how accurate these models will be. And yeah, the last part.
Sorry, can I ask, or should I just proceed?
Go ahead.
Just proceed.
Okay. Then, sorry. Then, me?
Go ahead. That was the last point.
Oh, okay. Sorry. Yeah. The last. Yeah. The last one is my idea. Basically, well, the question is whether it is applicable to neural ODE. Well, if you remember the ODE session, then I think most of you agree that ODE right now has no built-in equivariance. Yet there are many ways to reinforce it. For example, that dot augmentation is one way. And so the question is, how do we do it without an augmentation?
That's mainly. Does anyone else have any kind of questions? Or?
Okay, let us thank you first, and then we'll ask the question.
So one thing that has not been touched on is scale, zooming in, zooming out. Yes, you can take care of translation. The Welling paper, Max Welling paper takes care sort of rotations, kind of.
Yeah.
Okay. But what about scale, like zooming in, zooming out? What about trying to find out somehow a representation of boundaries of objects too? I guess these are the two questions that I have in general.
For the first question, I think I have an answer. The original, well, harmonic net paper does not touch scaling, but it can be made easy. Remember the extra dimension on the radial domain? You can simply add an extra pooling there.
Yes, but at the same time, the issue with scale is that as you zoom in and you keep the filter size the same, you tend to lose a lot of information, and whatever that was high frequency becomes low frequency. So I can see the features being not very robust to these kinds of changes.
Oh, I see. So basically, it's like, you know, if the integration path is first zooming into a very small point and then keep at that scale, comparing to the information to the path that takes, you know, first you don't zoom in, and then at the last step, it usually loses a lot of information, or what we call fidelity.
Yeah.
That this information becomes kind of useless.
Pretty much.
Oh, well, to be honest, that's kind of a numerical problem that.
But we don't have it.
But yeah, it's
Yeah, this paper didn't really.
Yeah, that-
But yeah, it would definitely change the results, because like the way that they were showing in examples of like what like there's 3D representations of what those spherical convolutions are. If you were to change the scale of it, it would like dramatically change the output. So
The frequency would literally mean a different thing. is what
yeah,
you're saying.
that's exactly what I mean. Frequency is just going to be something very different. It's an impression that's not robust, at least to that.
But scale invariance is also like probably the hardest problem.
I
So
think
that
so.
you're not being very generous.
No reason to be.
So
I don't know that, seriously.
So I just want to be where it applies. So for the protein example, does it still apply there, or it's just for the images, the scaling variance problem?
no, it would still apply to the protein
Well,
problem too.
For protein problem, scaling doesn't exist because it's already in 3D. It doesn't have the, you know, the camera projection.
So it's not, because what I understood that it wasn't an image, or was it?
No,
I thought it was
wasn't.
just a
The
combination of
harmonic-
vectors.
The harmonic network, the predecessor of the tensor field network applies to image in 2D. This paper, the present one, simply pushed that idea to an extremity, from 3D 2D rotation plus 2D translation to 1D rotation to the extremity to 6D.
But scaling is still applies,
that's
right?
that's full scale Euclidean.
Still applies?
Euclidean space.
Well, one thing that kind of helped me when I was looking through the code to understand how the spherical convolution system works is that you have to define like an origin point, right? And depending on how you define what that is, it could really change the output of like how, let's say, that convolution worked. And so if it makes that much of a difference in terms of where the origin is, like you can see how like the scale and like making the radius longer will definitely like impact, like making a major impact on like the output.
So is it 2D or 3D?
3D.
3D, yeah.
Oh, but in 3D, scaling problem doesn't exist, right?
Why not?
If you push two molecule too close to each other, then they're expelled.
No, but you do like that to all the space, right? So
All the space.
like if you do a scaling of all the space, I think that just like changing the scale.
You
right?
mean on different layer or
changing the unit of measure. So it's like it should be symmetric.
You mean on different layers or on the same layer?
Or like for the input, for instance.
For the input, if your input is just a very big molecule with atoms, then the mutual distances between those atoms are controlled by by the force, right?
You're absolutely right, but I think I think we're rabbit holing a bit here. But like the issue is really just to say that when you train the network, it's expecting a particular relationship. So if you radically change the scale, you would expect that the network would behave strangely.
You don't really have to radically actually.
Or it could be small.
I see.
It doesn't have to be that big. Yeah.
Yeah.
So this case doesn't exist for 3D, but you're asking anyway.
Well, maybe not molecules.
But I can, like, if I took the planet Earth and anyway, I think we can move to it. We can talk about this more afterwards, but.
Okay, let's see if there are any other questions.
I have a couple. First one, you mentioned about that regarding of the kernel in the frequency domain. The size of the parameters is way less. I guess one slide before this one. So that the size of why is that? Why the number of the parameters is way less than the normal convolution?
Yeah. So like in terms of like when you're creating a function that generates like a frequency, like let's say you're trying to, it's kind of like when you're doing like Fourier analysis for figuring out like a function that can graph out like a set of points, right? That you can see that there's a lot of symmetries in the sphere itself. That these points will be plugged into a function that essentially means that when you get your x, y, and z coordinate and put it into the function that has these parameters, it'll create like the weights that you multiply your point with. And that's like a lot different than, let's say, for like a convolution kernel where you have to define all of like the weights for every single.
If I'm not mistaken, you mean that in the mathematical formula, the number of the coefficient that we are going to store for each kernel can be way less than compared to the number of the parameters that you have in the kernel. But that's what you mean?
Yeah, and it's a lot easier to see in when it's only 2 dimensions, not in 3 dimensions, right? Because, for example, this is only storing like one parameter, right? So, whereas this one, every single like pixel for the kernel, it'll have to store like a parameter. So you only have to work with like a small fraction of the parameters you have to work with in a traditional sense.
Can I add something? I think this illustration of Fourier base is kind of misleading because it deliberately omits the radial part. So I would prefer.
You're answering my second question. I'm asking for
I would prefer this this illustration. It looks way better. So basically means the number of coefficients becomes less, but not too much less. You only have like, for example, if the conventional filter has 2 dimensions, and now you're converted to radio, which is still very big, and frequency, which is 0 and 1. That is small, but each part contains the real part and the imaginary part, and it becomes not that small.
Regarding the second one, I want to know that what's your idea? The paper that won the best paper for the last year from the Google, same group. They had a discussion regarding the data that is stored in each point that you are mentioning. The first bit. Did you have a chance to check that paper, and what do you think about that paper?
Each point?
The data that is stored in the point that you are in the point.
That's what we had as our discussion point.
The discussion point, yeah.
Like there seems like there could be so much like analysis into the vector that you store with the points. But I guess that's probably the
first one that you mentioned. I know that paper has a discussion there regarding that in their approach, that what data that they are storing in each point. So, did you have a chance to check that paper?
No. I didn't, but my instinct is that are they like colors on the pixels?
They show that the points are really have a tendency to go to find the corners of the objects, whatever that you have it on the thing. So, or that's the approach that those guys using it. Also, I wonder that you said that you had JPEG, you had the GIF file that you want to show us.
Yeah,
it's possible.
Yeah, I think you almost see it.
In the Slack, I'm going to post a video. Like the video where this comes from is like incredible in the sense that it's this person presenting this paper that first came up with this idea. He goes through a 5-minute video, like intuitively showing you like all these animations as to how something like this paper works, and that's where all the gifts come from. It's just like this 5-minute video of like animations just like that, one after another.
I'll ask one question. So, in the earlier part in Peng's talk,
yes,
you had, I don't know, it's like time passed by and I forgot most of it, but you use autoencoder and then you said, because I'm using autoencoders, then it's equivariance or?
Yeah, when you're, only the first input and the last output, the final output of the autoencoder will abide, plane equivariance, but not group equivariance.
What does the autoencoder do? What's the input, what's the output of the autoencoder?
Input is an image, output is the same image. So if you move the original image, you have to move the output image, otherwise it doesn't make sense. And if you want to enforce the network to do that, that's then all the layers together as an entity must have the plane equivariance property.
As opposed to individual layers.
Yes, exactly. For individual layers, the group equivariance property is a much more relaxed condition.
So I think what I'm trying to understand is that you're feeding a few images that I assume are augmented of one.
Yes.
So like you augment this one image into a few rotations of it.
Yes.
You feed it to the autoencoder. They're different instances. How do you connect? How does your basically your autoencoder is forming a representation for all these different inputs. Does it have?
You're asking different. Your answer is you're asking different questions, or you're answering a different question. You're saying different things.
So I don't think so. So all I've been asking is that how does your autoencoder help with the equivariance problem? Because you're still feeding in, from my understanding.
Yeah. Because
so just to qualify, what I'm hearing you say is that you're saying in terms, because your original question was about if I have a 5 and then I have a 5 rotated, the underlying representation is actually distinct, autoencoder or no. It actually is representing to a different point in the higher dimensional space, right? Is that what you were, wasn't that sort of your question?
So the 5-1 and 5-2 that's rotated.
Yeah, they actually mean different things.
There is a disconnect between the two. Yes. So
Right.
to the autoencoder, you have two different representations.
So that's his question.
So you have two different representations. But what I think I'm hearing is that you have one representation that's invariant over rotation, or equivariant over rotation. How?
Well, I think the two concepts needs to be separated. They sound similar. The plane equivariance and the group equivariance. Plane equivariance means, if you do something on the input, you do exactly the same thing on the output. That's not the case for each individual layer. And the group equivariance is you do something to the input, and you do something slightly, not something different, but you must do something to the output. And that something must somehow eventually can be reconstructed through the other layer, through the, the generator layer of the autoencoder. So, by enforcing that weak group equivariance, you make the strong equivariance in the initial input layer and the final output layer possible.
So it's almost like sort of saying that if you, it's almost a claim similar to like the Wasserstein-Gann thing, where they're saying the types of functions that you can learn are easier to learn if they're whatever, K-Lipsch, whatever. So it's sort of like saying, if you're, but the Lipsch constraint is a different constraint. Here, the pitch is, if you have these constraints over your network activations in the intermediary layers that have a group structure, then you just get the final state for free, almost. Or it's easier to train, or I don't know, something to this extent.
So
does that make sense, or am I way out to lunch?
Well, again, I prefer not to make assumption on what that group is. It could possibly include all possible, augmentation, including dumping some kind of, the watermark of a rabbit on top of it.
Yeah.
But yeah,
because group structures are actually very weak, is your point.
Yeah, exactly. But the idea is that, this is basically an argument against invariant feature. Because if you do something to the input and you don't have to do anything to the output, then it is almost impossible for the generator part to infer the original image. It's just, it just doesn't make sense. It's like, if you don't have anything in, then there will be nothing out.
Okay,
So
great.
basically, yeah.
With that, I'd like to end the session. Thank you very much. We've been over an hour. All right, thank you so much.
Hi, I'm Serena. I'm on the TDLS steering committee. I hope you enjoyed our session. Please subscribe, check out our live streams, and check out the other content on our channel.